tomorrow, and then I'm taking the cars section. I'm retaking it technically. On Saturday when I take my Jack Wesson full length one.
How did you do on the BB?
I got a 128. So I retook it, but like I barely remembered anything. Like we went over a couple of the questions, but
Yeah.
um yeah, I got a 128. The alarming part is when I took Chem Phys again, I got a 126 again. That was really alarming. So today we're going over section bank for Chem Phys and like I'm ready.
Yep.
110% concentration like for the session. So because Chem Phys, it's alarming. I mean, it's 3 months of prep and I didn't go up a point and I retook the section.
Mhm.
So
Got it. Yeah, so yeah, we can go over this, but from that CP section, I would look at the questions that you're getting wrong and then see what topic that stuff is based on and see if it's a topic related issue. Uh, we can do that, you know, later though.
there were 6 questions
Yeah.
in Chem Phys. The ID noted were pretty stupid questions. I literally wrongly multiplied units in one of them. And another, I like just missed the fact that I needed to use meters instead of centimeters.
So calculation problems are some of these CP questions, right?
Yes, there were at least 3 that were calculation, like
Okay.
stupid mistakes.
That's good to know because that's one of the things that, you know, when we've been going over stuff, we kind of brush through like the calculation part. So from now on, I'm gonna have you more so do the calculation.
Okay.
Because yeah, like you can Anki most things, but actual like calculation stuff takes just straight up putting pen to paper and actually doing like the work and practice. So yeah, we're gonna have you do some more calculation problems.
Okay.
Because yeah, you don't want to make those types of mistakes with, units and things like that. But at least we know that now. So we know what to work on from that CP section. And all right, awesome, cool.
Let's get into it.
Probably even send you like, well, Jack Weston, I don't know if they have it anymore, but they used to have like math sets,
Mhm.
like discrete questions that are,
Yeah.
yeah, but I don't know if they have them anymore, but or maybe they're called something else. I think they're called physical discrete set.
Mhm.
So those would be good to do. I would.
Okay.
Yep.
Yeah, yeah, yeah.
So okay, let's do that passage.
Mhm.
So Bitcoin might hit 100,000, I think, by tonight, maybe.
You got big stakes in that?
Yep. Yeah.
Uh,
Yeah. It's crazy.
It's
Right after Trump got elected, it just
really
yeah, yeah. Hmm.
wow. I don't even know. I don't know much about crypto. So my roommate from freshman year was like
Hmm.
whole nother level. He's insane, knows everything, but
Yeah, yeah.
I'm the opposite.
That's a big part of like not just crypto, but like with stocks and like options and
Hmm.
stuff. I love it. Really exciting stuff.
Okay. Photoacoustic calorimetry.
So
Um,
what is
yeah.
calorimetry?
Yeah, it's gonna be I think a big part of our session today, but it's one of my lesser suits. Like from what I understand, calorimetry is when you have a substance and you put that substance in water and the change in temperature that you observe of the water is like it's like the heat. Um, I know there's bomb calorimetry and the other one,
Yeah, so
but
I think of it as a way, like let's say you have a candy bar and on the back it tells you the calories on it, right? How do we know that, right?
Mhm.
So let's start with a bomb calorimeter. So I kind of drew something like that here, and this. So I kind of drew this container, and the blue is water around it. And let's say in this container, we put in the candy bar and we combust it. So it kind of like whatever, let's say explodes or something. And it's going to cause that heat to be released and absorbed by the walls of the container. And that'll get heated up. And then it'll heat up the water as well. And what we would see would be a change in the temperature of the water. So that means that, you know, Q being the heat energy equals MC delta T. This is the mass of the water, the specific heat of the water, which is basically like the heat capacity of water, which are known. The mass will be known, the specific heat will be known. And then we read the temperature change on the thermometer to know the delta T, and that will give us the heat energy here.
Mhm.
Okay. So um that's the bomb calorimeter. But generally what a calorimeter does is it it helps you figure out the energy of bonds of whatever thing that you're trying to find the energy of the bonds of. Okay.
Mhm. Yes.
So okay.
Does the MCAT expect us to know the difference between the bomb calorimetry and the other one?
Well, when you say the other one,
I don't know it. I forgot
so
the name.
so the bomb calorimeter, yes. This is introducing a different type of calorimetry technique that they will tell us about because we're not expected to know like this type of calorimetry technique. But we do want to know like what a calorimeter basically does. And then yes, what I drew, the bomb calorimeter, you need to know that. Uh yeah.
The one I spoke about was the coffee cup calorimeter. That's what I was referring to.
Oh yeah, that's pretty much like the same thing.
Oh,
Same principle. Uh you just put it in, a styrofoam cup and that doesn't let heat escape. Um, Same thing here. This is just with, just made of metal, I guess. With that. But yeah, yeah. So essentially, you use water and a thermometer in these two techniques to figure out based on the change in temperature of the water. We know everything else about the water, and we can figure out the heat in something based on that.
all right.
All right, why don't you read this? Yep.
Photoacoustic calorimetry is a technique used to determine the bond dissociation enthalpy of solute molecules. PAC is based on the photoacoustic effect, in which matter emits sound after it has absorbed light. Photoacoustic calorimeter schematic is shown in Figure 1.
All right, describe to me what you see here.
Um, Shine a laser into a lens. It's a converging lens.
Okay.
Um, because like the rays converge at a point, and the sample is like the object which you will focus on.
When you say object,
Sample. I mean,
the thing you're trying to find the bond energy of, right?
okay, yeah, yeah, yeah.
So we have
And then, mhm.
Uh-huh. What were you gonna say?
Um, and then it emits, I mean, energy that we can read the energy.
Yeah, so far we just see that okay, there's a microphone and an oscilloscope and some type of energy meter, but yeah, we can, continue reading to learn more about that.
Mhm. Okay. The monochromatic pulsed laser beam is focused on a sample cell using a thin lens. Each photon causes the cleavage of a chemical bond in the solute molecules. Because the photon energy is designed to be larger than the energy needed to break the bond, the excess energy is absorbed by the solution, causing a local temperature increase. This fast and localized heating process creates a sound wave that reaches the microphone, which sends the sound to an oscilloscope for recording. The amplitude of the sound signal is proportional to the amount of heat produced, delta H and R. The energy meter, based on the photoelectric effect, uses a detector with the work function of 3.4 electrovolts.
Okay, what's this mean?
My guess is that it's one color.
Yeah, which would mean like one wavelength, right?
Sure.
Okay, what about
What is chrome? Chromatic.
um I'm gonna guess Greek for color.
Okay.
Yep, Greek for color.
Okay. Um, got it.
All right, I was gonna ask, so this amplitude here, right? Now, does that mean you have like a high wavelength or a high frequency or anything like that?
I think of amplitude as intensity,
Okay,
and intensity is based on number of photons.
okay.
So number of photons proportional to the amount of energy.
So, so this is like kind of like when we talked before about amplitude is the vertical portion, whereas wavelength is the horizontal.
Yeah, and they're not related.
Yeah. Now, same thing with frequency, which is also horizontal, and speed.
Yes.
None of that stuff is related to amplitude.
Okay.
Right. And now for amplitude being intensity, uh, amplitude will be whatever it is depending on the situation. So here they're just saying the amplitude is proportional to the amount of heat that's produced. So it's not exactly um, intensity here.
Okay.
Okay. Now, okay, so now we have some more information about the microphone and the oscilloscope here. So if we look back at figure one, maybe now we can explain what happens there. So what happens there? Like when you know, so you have your sample is going to be something that you're trying to, some molecule that you're trying to break apart, right? And when you do that, what happens?
So you break the bonds in it and any excess energy um is transferred, it's like transferred into a sound wave
Yeah.
and the microphone catches that sound wave um and records it.
Yep, the oscilloscope records it. So okay. So just the in-between part. So the photon hits it, a photon with higher, high enough energy to cleave the bond. It creates some bit of excess energy that's absorbed by the solution, right? Because we're breaking the solute bonds. So it makes some excess energy, which is absorbed by the solution, causing that local temperature increase, which then turns into a sound wave which then reaches the microphone, which picks it up, and the oscilloscope records it. And that sound wave's amplitude is going to be proportional to that heat, that excess heat that's produced, that's absorbed.
Mhm.
Now, in the bomb calorimeter, they also have this water around it, absorbing it. So why are they doing it for this one? Is it exactly the same or maybe something is a little different about it?
What do you mean?
So in the bomb calorimeter, we have our cleavage of the bonds and the localized heat the heat transfer goes to the water surrounding it, and then we measure, the change in temperature. So this one, is this the same or is this perhaps a little different?
I think it's the same.
So, um, let's see. Okay, we can go with that for now. All right, you can
Okay.
continue reading.
The energy in the photochemical reaction, delta HU, is the difference between the laser pulse energy EM and the heat detected HNR. The bond enthalpy is determined as the ratio between delta HU and the efficiency of the photochemical process. Table 1 summarizes the values of the bond association enthalpy of OH bonds and phenols, SH bonds and thiophenols, and CH bonds and alkyl benzenes, and corresponding types of lasers used.
What does this look like?
Our aromatic ring, thiophenol aromatic ring with SH, alkyl benzene,
Well, tell me more about because you could have lots of aromatic ring can mean lots of things, but
6 carbon ring with conjugation.
that's it.
Oh, OH, with the OH group, OH group.
Good, good, good. Does that sound like any or does that look like any type of amino acid?
Yeah, it's tyrosine.
Very good. And then what's that?
It's a well, um, well, there's the SH group,
Hmm.
and also it's like a phenol. So I guess there's an SH group on a aromatic ring with also an OH group.
So what I think it could mean is just it's the same thing as the phenol, but you just have a SH instead of the OH.
Oh, okay, okay.
Because yeah, the thio part is sulfur.
Yeah,
Um, these could also theoretically form disulfide bonds.
like the thiophenols with each other. Yeah,
Yeah, right? Like cis.
yeah.
All right. What about alkyl benzene?
Benzene isn't it also like a ring, aromatic ring, but the alkyl is just like CH3.
Yep.
Well, I mean, it could be anything. It could be like propyl,
That,
whatever, methyl.
that's true. So yeah, the PHEN means benzene, same thing.
Uh-huh.
So if you had, for instance, phenyl, it just means a benzene, like
Okay.
benzene attached. Yeah. Okay. And then we see table one. What do we see there?
We see the different bonds
Mhm.
and their respective enthalpies. So that's like how much energy is in the bond, and I guess the type of laser used to break it. Yeah.
Got it. Um, so which of these bonds is the shortest?
Um, I mean, it would take probably the least energy to break the longest bond.
Okay. So,
Least energy to break the longest bond. So shortest is OH.
yep, meaning yeah, most energy. Good, 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 good. All right, let's do it. So let's any questions though so far?
I mean, they'll probably come up as we go through this, but yeah.
Okay.
Based on the passage, an experimental feature that distinguishes PAC technique from the classic calorimetry technique based on thermometers is that PAC. Okay. Can be used on samples with specific heats larger than waters. Um, okay, enables the wait, so I guess you want to go first through A, right?
What is the classic calorimetry technique based on thermometers?
Is it bomb calorimetry?
Yep. Or the styrofoam one, but yeah. Hmm.
Okay. And
Yeah.
hmm, does it say what our solution is in the KC? Like, no.
Hmm.
I was a little clueless with A. I mean, um, like we're not supposed to know any other specific heats, obviously.
You said we're not
I was a little clueless with A because I wasn't sure about this, like specific heats. Like we're not supposed to know any other specific heats.
Oh, uh well, we know that the regular or the classic calorimetry technique is dependent on specific heat, right?
Sure.
But for pack, they don't really mention anything about specific heat, right?
Okay.
So, because what they're doing in pack is they're they're turning instead of measuring the heat directly, they are using sound as like a proxy. So specific heats larger than waters doesn't seem like specific heat is a factor here for pack, right?
You know what I don't understand? What's the point of all this if it's measuring just the excess energy? Like, aren't we trying to measure all the energy?
So that could be a little confusing. So it's really like it's not like a significant amount of excess energy. Like I would say like to even think of it as like a very, very tiny addition of energy, not like a really high amount. So the reason that it's like that is just because when you break the bond, you have a little bit of excess energy that creates that fast localized heat, which then gets to turn into a sound wave that you get to record and then use as a proxy for the heat. So the excess energy, just think of it as like a tiny bit. Like I wouldn't even like if it was 463, like maybe like zero point 0.1 or something, like some tiny amount.
Okay. So A is wrong because we don't talk about specific heat here.
Uh, so technically speaking, if we had this bomb calorimeter, we should, there's nothing that says that we can't use a different liquid, because if you use a different liquid and then you use the mass of the liquid and the specific heat of that liquid, you could still do it. So it's not saying that the classic technique can't do it. So that's one reason A can be wrong. Another reason can be that what they described to us doesn't seem to mention anything about specific heat. Like it's not a factor in this type of pack calorimetry.
Mhm.
So, you know, so what we want to think of is how is this different from this?
Yeah.
And it's kind of related to something I was asking you a little bit earlier.
Yeah. Um, so B, the issues, I think I remember this was the answer, so I'm getting biased a bit. But um, so we'll leave that. But first I guess we'll go through C and D.
Okay.
Um, C is based on the second law of thermodynamics. I don't even remember that. Yeah. Is second law that everything goes from um to high at entropy?
Yep. And the entropy of the universe um is always increasing.
How about the first law? Is that Q minus W?
Yeah.
Delta U equals Q minus W. Okay. The zeroth law is like an object is touching another object, like it's I forget actually.
Yeah. If two systems are in equilibrium with a third system, um, so is the third system. They're all in thermal equilibrium with each other.
All right, so the second law is based on increasing entropy, and that I mean, yeah, I mean that's very out of scope, I feel like.
Hmm.
So C is a lot easier to eliminate than A for me. D used on samples in the solid phase only. So I mean only is red flag, but um why would you eliminate D? Because I mean here we see a sample that it doesn't tell us it's a solute molecules.
Yeah. So, um, that could be considered to be a solid, but if it's a solute, it means it's in a solution, which means that there's a solvent there. So you would still need uh something to be in the liquid phase.
Yeah.
So, so D wouldn't work.
Hmm.
And so what I was asking before was in our regular bomb calorimeter, it seems like it's the same thing. Heat causes an increase in the water temperature, right?
Sure.
And here they're saying, the solution also similar to it, except a little different.
But what is the difference between, aren't they both fast and localized heat processes? The calorimeter and the pack?
imagine this thermometer. Let's say we moved it here or anywhere. We should still have like nothing should change. So what's the implication of that?
That it's fast,
So let's say it's
non-localized.
yep, yep. Because the thermometer could be anywhere. Doesn't matter because what the heat from breaking this bond heats up that entire like container of water, and that's delocalized. But pack has a localized temperature increase, which then turns into sound,
Mhm.
right?
Huh. How about fast? Is bomb calorimetry slow?
Like, I would say so, yeah, because it will take some time for the heat to reach wherever that thermometer is, right? And maybe we want to place the thermometer closer to it to maybe make it go faster, but it's not going to change the results. So a regular calorimeter is not going to have a fast or localized heat transfer process. It's going to be delocalized, like in the general area, but it's really the temperature of the entire all of the water would increase here. Whereas here it would be like just localized to that environment. That's the key difference.
Mhm.
Yeah.
So you're saying bomb calorimetry is slow, it takes time for heat to reach the thermometer.
Uh, Also, I would say also to put in that it's delocalized and um, so
Wait, bomb calorimetry is localized, no?
delocalized.
Bomb calorimetry is delocalized. Oh yeah, right, because you can put it anywhere.
Mhm.
Okay.
Yeah. So what can help here is that okay, we are taught bomb calorimetry, but they never teach you that it's slow and delocalized. So why are we saying that now? Because when they're saying pack is fast and localized, we know that about pack. And since we never said that about the bomb calorimeter, it must not be what happens in the bomb calorimeter.
Yeah. Yeah. Okay. All right, I'm writing some notes. Okay, so got you.
Okay. Now this question everyone gets wrong, and it's because they don't tell us anything about the energy meter aside from its work function. Now, let's approach it this way. Let's say, so they're asking when an appropriate laser is used, right? Let's
Mhm.
see what happens if an inappropriate laser is used. For instance, let's say that we use laser A, but inside of our sample, we have an SH bond. Okay. So laser A, 463 I'm gonna forget out the mole part right now. 463 kilojoules, right? Um, how much do you need to break the SH bond?
349.
Okay. So what would happen if we use laser A for the SH bond? Um, yeah.
We're using more energy than we need.
Okay. Now, they did say that there's some excess energy that's absorbed by the solution and blah blah blah, but that's excess energy like from that solute molecule chemical bond breaking. But once it's already broken and that excess energy is already, caused that temperature increase and blah blah blah, what happens to the rest of that energy from the laser?
You know, I guess it is like released as photons.
Yep. Or maybe it doesn't even change into not a photon, right? Because the first 349 kilojoules worth of photons go to destroy the SH bond and then produce that, sound signal and stuff. What happens to the rest? Like, what is this? Like 123 or 124 kilojoules that are left? That won't be absorbed here because you've already destroyed the bond. So maybe that's what you would see here.
So why again isn't it photons
No, no.
that
So
get released?
it is photons, but it's not that. So, okay, so first we're shooting photons from the laser, and the photons hit the solute molecules, and it's exactly like what we talked about yesterday with like absorb the solute molecules will absorb the energy of the photon. And if it's a high enough energy, it can break the bonds of that solute molecule.
Mhm.
So that's going to be photons being absorbed by the, solute, causing bonds to break and all that stuff, right? Now, the extra 124 kilojoules, if you use laser A for an SH bond, this stuff doesn't get picked up by the sample. The sample's already taken in as much energy as it can. So maybe that's what these arrows that continue to go past the sample indicate.
Mhm.
These are still photons. It's not like they've turned into energy that breaks the bond and then turned back into photons. They have never not been photons. They stay photons.
Mhm.
Okay. So the energy meter is a way for us to account for everything, right?
Okay.
So like yeah, if we had this, but we used this laser, you would see on the energy meter the difference 124. And that lets us account for everything. If like let's say we didn't have it, right? If we didn't have it, how would we know that this is the bond energy of the SH bond? Because if we use laser A with this much bond with this much energy for the laser A, it would break the SH bond, right?
Yeah, but then how like scientists find like the original one, you know?
That's where the energy meter comes in, right? Because that lets us see. So, like, if we use laser A without the energy meter, we're going to be like, okay, SH bond requires 463 kilojoules per mole. But if we have the energy meter and we use laser A and we see, oh, 124 kilojoules on the energy meter, that means 463 minus 124 is the energy of this bond that we broke.
Mhm.
So It's there to account for everything.
Got it.
Yeah. So that's why I started off by asking, what if we used an inappropriate laser,
Hmm.
right?
Hmm.
So now the question's asking, what if you used an appropriate laser? So let's say for the SH bond, you use laser C.
Yeah, it'll be zero.
Yep.
So if we're the AMC, why do we use A, B, and C? Is that fully just to confuse you, or like what?
Oh no, if it's so if you have an OH bond, you're going to need to use laser A. If you use laser B, it's not going to work, right? So like to break this bond,
No,
right?
I'm saying I meant answer choices A, B, and C. Like,
Oh,
is there any relation?
sorry. I thought you meant laser A, B, and C.
Yeah, yeah, that's my fault. I should clarify.
No, so sorry, you're asking what's the
Like, I guess I'm just trying to think of like the test creators' perspectives. I guess like
oh, like why they made those
they
choices.
just yeah. I mean, I guess because they mentioned those three, right?
Yeah, because like 99% like of the time, whenever a student of mine like on average like eliminates an answer choice, they're gonna say this is the reason. They're gonna say it wasn't mentioned in the passage. That's like 99% of the time what people say, which means that 99% of the time people choose answers that are in the passage. So
Hmm.
why do they make these choices? Because
Yeah,
they're in the passage.
right.
And people on average will be like, it can't be zero because they didn't say that in the passage. So that's the test taking thing there.
Hmm. Okay. So if it's a non-appropriate laser, then there would be some sort of reading and energy meter.
Mhm. Yeah, you could even actually find the actual amount, which would just be this.
Mhm. Okay.
But yeah. And also, you know, um, yeah, I guess a lot of times on the AMC, it's like gonna be just there's a lot of things that just won't explicitly be said. Um, so that's why that question was tough. But
Okay. Question nine. This is just for the principal. Uh, it's A, right? Because
uh-huh.
I mean, the phenol slash benzene,
Hmm.
or yeah, they have the aromatic rings,
Hmm. Yeah.
and yeah, so it's A. Um, an alkyl is just a methyl or propyl or butyl or
Yep.
right. Okay. Next. According to the passage in the data in table one, what feature must distinguish laser type A from laser type B in order to be suitable for the cleavage of the bonds specified? Laser A, laser type A must. Okay. Um, so okay. Uh, fire proofs.
What's different between the lasers?
The enthalpy,
So,
it's how like the energy stored inside the bond that they're breaking.
yep. So we just say that the lasers are different in energy, right?
Yes.
Okay.
And I remember what I was thinking when I took this.
Hmm.
I put A which I think was just out of scope. Because I thought, because there's more energy in the OH bond, we have to make sure it like focuses more, you know, so it can be a little more efficient at breaking the bond.
Okay.
But that's what I remember.
So we know also from yesterday that a photon's energy is there's like a formula for it, right?
E equals HF.
Okay. And
Yeah.
what if you didn't have F?
It would be E equals HC over lambda.
Okay. So we know that energy has something to do with frequency and wavelength, right?
Yeah.
So what about emit fewer photons? Or what if it even said more photons? What would that be?
More photons.
Hmm.
That would be like intensity
Is intensity
slash amplitude,
uh
kinda.
so is intensity energy?
It's related to energy.
Mm.
Energy over time.
Yeah, in this one they're saying per unit time. But the number
Oh
of
yeah.
yeah, but don't worry about that right now. But the number of photons is intensity, right?
Number of photons is correlated to intensity, yeah. Related.
Uh, which could correspond to increase in brightness. And the actual unit is power over area. So if something's better focused, that would be reducing the area, right? So
Hmm.
this would be an increase in intensity, and then this one would be a decrease in intensity. But intensity is not energy. They don't have anything to do with one another. So
Intensity doesn't have anything to do with energy.
correct. Because the energy has to do with a photon's frequency, which means that, it has to do with the photon's wavelength. But intensity is how many of the photons you have. So if you have 10 trillion photons with, you know, 375 as your energy, all tr those trillions of photons won't be able to break an OH bond, whereas one photon of energy 463 would be able to. And Um, and they always like to ask this type of question where it's like they ask you something about the photon's energy, and then in the choices, you'll always see something that says in one word, in many different types of words, intensity. But intensity is not going to be energy. You can think of intensity. So the things I guess you're writing in your Anki thing. So this is
Right
what
now, yeah, I'm just writing in my notes. Yeah, but yeah.
yeah. So I'll write for you. So basically, intent intensity equals number of photons, which corresponds to brightness. For sound, it would be number of sound waves, and this corresponds to loudness. Um, Unit is power over area or watts per square meter. So, so that's also why, uh, you know, in a regular day with the sun, it's hottest when the sun is directly above you. If the sun is at an angle, it spreads that light across a larger area compared to if the sun was directly overhead. it concentrates it all in a smaller area. So while the number of photons for this sun example doesn't change, the area does change. So that's why, like, at 12 noon or whatever will typically be the hottest time of the day. That's also why in the winter we are actually closer to the sun than in the summer when we're further from the sun. It's just that in the winter, or rather in the summer, we're angled towards the sun, which would be like this example.
But if we're angled towards the sun, why is it above us?
Oh, sorry. In this example that I drew?
I'm saying you said during the winter,
Oh, yeah. Sorry.
but
In during the winter,
we're
we
angled.
angled away.
Oh, okay. Yeah, yeah. Okay.
Yeah. And during the summer, we're angled toward. So,
So the noon is the hottest part of the day because like the sun is right above you.
yes.
It's a smaller amount of an area, or
Yeah. Compared to if it was hitting from the side, it would at an oblique angle, it will have a larger area, be spread apart across a larger area.
so like basically if something is better focused, it's focused on a smaller area, which means intensity goes up.
Hmm. Yep. Have you ever like used a magnifying glass to burn stuff?
No, but
That's what you do
it's
because
all yeah.
the object is the sun and the converging lens of the magnifying glass concentrates it at a tiny, tiny point, which means the intensity is up. We're not really changing the number of photons, but we're making the area change, which means that the intensity can change as well.
Okay. If D said higher amount of photons,
Mhm.
then what?
Still, his number of photons is intensity, but
Right.
energy is like, I don't want to say like something you're born with, but a photon, its energy is something that it's born with. Um, so if you don't have enough energy, it doesn't matter how many of you there are, you know? Um, so, if you have a lot of photons, you could get a really bright, like, light, but it's not going to be a higher energy light. Because if you have a higher energy light, you can get like ionizing radiation and stuff, right?
Okay.
So, yeah. So number of photons is intensity, and they're adding the per unit time thing, which would just be intensity per whatever time. So that would be like this times, whatever, let's say seconds on the bottom. But ultimately, the only thing, a photon's energy is related to its frequency and its wavelength because all of those things are related. But yeah, you can't change that. You know, you can't change a photon can't change its energy.
Mhm. Okay. And C, if it said shorter like wavelength, that could be right.
Yeah,
Um,
it'll have something to do with these. Mhm.
hmm, okay.
Laser actually stands for light amplification from stimulation of emitted radiation. I think that's what it is. Stands for.
That I'm gonna remember it, but
Mhm.
yeah. Okay. Well, I didn't even know that like that was an acronym. So
Yep.
nice. Okay. Got it. So E equals HF basically is this what they are testing here,
Hmm.
just in general. All right. This I got right. So like,
Yeah.
this was like very, very like elementary, just 1 over F equals 1 over Ti plus 1 over Do.
Yeah. Now, also, you didn't even have to really do the math here. Remember what I said about reciprocal sums? And
Oh,
that answer must be smaller than either of these. The only one that's smaller is that one. So, I mean, of
mm,
course, do the math,
yeah.
make sure, but also,
With my track record on doing math recently, trust me, I would do it 3 times.
Yeah. So
But yeah, it's a good shortcut.
if you take the 12 centimeters, get it, you maybe do this already, but get into the habit of just writing 12 like E negative 2 meters. Like when you write it down, just have it in the right unit.
Okay.
Get into the habit of that. If you saw like 4 kilograms, I would write 4E3 grams. You know what I mean?
Hmm.
520 nanometers, just write, oops, 520 E negative 9 meters.
Yeah. Okay.
And then this is like, yeah, that last thing that we talked about yesterday. But yep.
Yeah. What is the kinetic energy of a photoelectron produced in an energy meter of the packed device when the frequency of an instant photon that is not absorbed in the solution? When the frequency of an instant photon does not absorb in the solution, F equals 5 times 10 to the 15 hertz. Okay. Um, so like I'm still having a little hard time wrapping my head around because the way I learned it through like UWorld before was like the work function and the um it was like KF equal like K max equals like HF minus W or something.
So let's say we have a piece of like aluminum, metal, aluminum foil, something like that here, and we just attached that sheet of metal to like current carrying wires and like a light bulb.
Hmm.
Let's say that we had some laser or whatever. Um, and we shoot the laser at this sheet of metal and the light turns on. What must be happening here?
The aluminum foil is like transferring electrons to
Sorry, say that again.
there's electrons traveling from the aluminum to through the wire to the light
Yeah,
bulb.
good. Which means electrons have to
Come
leave.
up.
Yeah. So, so the photoelectric effect is when you have photons whose energy exceeds the ionization energy, which we can call work function. And that excess energy, it's not just going to excite the electron, it'll eject the electron. And when you eject an electron, that electron will be moving and therefore have a kinetic energy.
So repeat that again. Sorry.
Yeah. So yesterday we talked about absorbing a photon, exciting an electron.
Yeah.
Now, your ionization energy is the energy you need to ionize something, right?
Yeah.
Strip off an electron, right?
Yes.
So if you had a photon whose energy is beyond that of the ionization energy of the atom, right? Then that electron isn't just going to be excited, it's going to be ejected. It's going to leave the atom. That atom will turn into an ion, and the electron will leave. It'll go elsewhere.
But so is the laser shooting something with higher energy?
Yeah, in order for this to happen, right? Like let's say the work function, so okay. Like um yeah, so that's what's happening here. Yeah. Like let's say that, you know, this energy of this okay, let's just say that we had two lasers. Um and this bottom laser, we know it has 3.3 electron volts, and we shoot it and we don't have the light bulb turn on. And then this one has 3.5 electron volts, and we shoot it and the light bulb turns on. That means that this one isn't high enough to be larger than the ionization energy, aka the work function. So
Hmm.
so kinetic energy of the electron is equal to the energy of the photon minus the work function. And so if we had 3.3 electron volts minus the work function of 3.4, like this is like negative something, right? So this isn't going to cause, like, it's going to be negative something, but like, kinetic energy can't be negative, but it essentially means that your electron is not moving. It's still bound. Okay. Um, let's say that photon's energy is actually equal to the work function, then your kinetic energy is zero, which means that the electron is no longer bound, right? But it's not, it has enough energy to be unbound, but not enough to actually move. But yes, if you had something with 3.5 electron volts, you get zero point 0.1 electron volts as the kinetic energy of the electron, which means that the electron is, in addition to being unbound, it's ejected and it moves with a speed.
And is the speed 0.2 electrovolts?
For
Hmm,
this,
yeah, what will the speed be?
when you say that, what do you mean exactly?
Wait. Kinetic energy is it's just the energy of the KE. What is that exactly?
Like when you say exact, like the kinetic energy of the electron, you're saying?
Yeah.
Oh yeah, so that just means that the electron is moving.
Hmm.
That means that, we would get this light bulb to turn on because it's moving,
Gotcha.
right? So like, uh, yeah. So basically, um, did I answer your question?
Sure. What is the
Yeah.
threshold frequency?
When you say threshold frequency, oh, you mean like the frequency in order to cause a photoelectron to be ejected, you're saying?
Probably, because I always hear like threshold frequency, work function, they're all related, and the I guess kinetic energy.
Uh-huh.
I
So
can never put it like all together.
got it. So really what we're talking about here are energies. So your kinetic energy of your electron, your energy of your photon, and then the work function is just an ionization energy, the energy it takes to eject, sorry, so like, let's say we had this thing from yesterday, and the third shell is the outermost shell. And so, the total energy for that is 3.4 electron volts. So that means that, if you have 3.4 exactly, your electron would go here, but technically it won't be bound anymore. So it won't be bound, but so it has enough energy to no longer be bound, but not enough energy to actually move.
Mhm.
Now, if we had something with like 3.5 electron volts, it's beyond the third shell. And the third shell is the outermost shell. So it's beyond the outermost shell, which means it's no longer part of the atom. And whatever excess energy it has, so it's used the 3.4 electron volts of energy from the photon to eject itself from the atom. And whatever excess energy there is goes towards the velocity of that electron, causing that electron to move.
So if we shine like a 3.6 volt laser, then 0.2 EV would, you
With
know,
kinetic energy of that electron, yeah.
mhm. What if we shined 3.3?
Then it won't like even uh get to the point where it's unbound.
Would we go to N equals 2?
Yeah,
But there would be excess energy.
that's true. But that's fine. Because we would have enough for the n is equal to 2, but we don't have enough for the n is equal to 3.
But it would be at N equals 2 and then what? Would it just chill there or would it go back to N equals 1 and emit light?
It'll absorb, so like let's say this is 1 electron volt. It'll absorb 1 electron volt to get to the n is equal to 2 shell, and it won't absorb anything else. So it's almost like here, right? If we have something with this much, or sorry, this much, energy, but we use this laser, it means that this laser, this much of it will get absorbed, and the rest of it won't get absorbed. And that's why we have that energy meter. So you can actually think about it that way. Like, for instance, if we had, you said 3.3, and this is like whatever the where the atom that we're shooting it at is, and then we have an energy meter here, it would be like this. It would be like 1 electron volt gets absorbed to bring it to the n is equal to 2 shell, and then 2.4 of the remaining would get picked up by the energy meter.
Okay.
So so it's like you shine the light on it and it'll absorb what it can absorb, and the rest of it just won't get absorbed.
Mhm.
So yeah, if you had like if you had 2 electron volts, it's still going to just get up to the n is equal to 2 shell, and the excess would go there for the energy meter.
Right. Okay.
Yeah.
So in terms of the question,
Hmm.
like
Oh, and then you see how it says not absorbed in the solution. So yeah, that's what I mean with, this thing.
mhm. um F is that, H is that, we multiply them then. So 5 times 4.1, um, basically, to get the energy.
Um, so you're saying the energy of the photon, right?
Yeah, E equals HF.
Okay.
So 4.1 times 5 is 20.5.
Okay.
20.5 gets shine. So lasers 20.5 photons.
Okay.
Yeah, 20.5 minus 3.4.
Hmm.
Because the work function, which is the ionization energy,
Hmm.
you need 3.4 to break that bond.
Hmm.
The rest of it gets caught. I mean, it gets read by the energy meter.
Yeah, sorry. So there's a caveat there. Sorry. That so what we're talking about with the photoelectric effect, that excess energy, instead of it being on the energy meter, it's gonna be uh that electron moving. That energy is gonna go towards the electron's kinetic energy.
Oh, oh,
Yeah.
and anything that's not packed.
Oh, yeah, and anything. So like in this example that I showed, we had that excess, right? Because it's an excess because it's this 3.3 is not enough to be to ionize it, right?
Yeah.
That's why it'll reach whatever level that it can. In this case, the n is equal to 2 shell, and the rest of it that's not absorbed will be on the energy meter. But let's say that we had 3.5, right? And we connected this to like some light bulb. 3.5 means 3.4 will get absorbed, and the excess, instead of that hitting the energy meter, that excess will be imparted onto the electrons themselves to give them kinetic energy to move. And they can
Hmm.
move through the wire and light up that light bulb.
Yeah. But in pack, it would be absorbed in the energy meter, but only in pack because pack has an energy meter. But usually there's not an energy meter.
That'll be true unless the photon has energy that's larger than this. Then it'll cause, some type of like ions to form there or something like that.
What do you mean larger than that?
Oh, like meaning this energy meter part, yeah. So like if the laser had energy larger than the work function, it's gonna cause electrons to start leaving.
Yeah, wouldn't they get caught by energy meter?
Uh, Not really. Like if anything, it'll be like because you're not gonna really have like electrons just shot through the air and stuff. So that's why in the examples where I'm talking about the photoelectric effect, I talk about the wire.
Okay, I'm not gonna lie, that made me a little more confused. So just to
Yeah,
make sure,
yeah, yeah.
basically, like, let's say, like, forget pack existed. Basically, just in general, when you have the aluminum foil, let's say the work function of aluminum foil is 5 eV. Now, let's say you have a laser and the laser shoots 5.5 eV. Now it hits the aluminum foil, which is a 5 eV work function, which is ionization energy. And there's 5.5 minus 5, and that's 0.5. That means the electrons, they're gonna have an energy of 0.5 eV,
Hmm.
and they're gonna travel and light the light bulb.
Yeah. So I wrote this out again over here to show that if you had a laser with so from n is equal to 1 to n is equal to 3 is 2.5 electron volts. Now let's say we had 2.3 electron volts. This is our sample. This is our energy meter. And I'm going to connect the sample to the light bulb. Okay. Now, the 2.3 electron volts is enough to excite the electron to the n is equal to 2 shell, which you only need 1 electron volt for, right?
Mhm.
Now, we don't have enough to get it all the way up to n is equal to 3. So it'll go up 1 electron volt. The rest of the 1.3 electron volts will be read here on the energy meter.
Oh, okay.
Okay. Now, if it's 2.6 electron volts, it's going to go beyond that outermost shell, which means that your excess energy is going to be imparted onto the electron itself, causing the electron to move, and then it can light this up.
Mhm.
So if we are talking about energy levels below the work function and we have some enough energy to go from one shell to the next, but not to the next one, that excess will be read by the energy meter. But if you have energy that's larger than the work function, then that will not go to the energy meter. It'll go towards the electron's energy. And you can also connect it to ionizing radiation. Because if you think about it, technically, if your energy is higher than the work function, you're ionizing that atom by causing the electron to be ejected. So that's what ionizing radiation does.
And now, how does fluorescence tie into this?
So fluorescence is you're not going to have any type of the electrons will own. So if you have photon energy equal to the work function, it'll cause the electron to be unbound. If it's greater than the work function, the electron will be ejected with some
Wait,
speed.
wait, wait.
Yeah.
Start from the beginning. I'll actually write this down.
Here, so
Sorry.
um energy, um if energy equals work function, electron will be excited and unbound, but have no speed. So, no movement. Now, if energy is greater than the work function, electron will not just be excited and unbound, but also move with speed. And then if energy of photon absorbed is greater than energy of photon emitted, you have fluorescence. Okay. So, and then if energy of photon absorbed equals energy of photon emitted, this is just the normal case, I guess. So starting from the bottom, if the energy of the photon absorbed equals the energy of the photon emitted, that's just the normal case with conservation of energy. If the energy of the photon absorbed is greater than the energy of the photon emitted, you have fluorescence. So that would be like if this photon gets absorbed and excited to the n is equal to 3 shell, through that molecule's resonant stabilization, it will enable the electron to relax down a step without having to emit a photon. But then when it goes down from 2 to 1, it will emit a photon. It's just that it took 2.5 electron volts to get here, but it takes 1 electron volt to get back to 1 from 2. So that's why in fluorescence, the absorbed energy of the photon is larger than the emitted photon.
So does fluorescence only happen in things that have resonance then, or what?
Yeah.
Okay, that makes some more sense.
Yep. If you look up chlorophyll, if you look up melanin, if you look up any type of dye, any type of pigment, you will see that they have extensive conjugation.
Hmm.
That's also why UV vis is a type of spectroscopy that you use to detect triple bonds, double bonds, conjugation, basically. And it's called UV vis because it absorbs the UV light, which is higher in energy, and it emits the visible light, which is lower in energy.
Read that.
Mhm. So, um, so I'm trying to think of what exactly.
Mm-hmm.
So okay, so the regular situation, photon gets absorbed equals photon energy of photon absorbed equals energy of photon emitted. Fluorescence, energy of photon absorbed will be larger than the energy of the photon emitted. And that is only true for molecules that have extensive conjugation, which is, oh, that's the UV vis. So, and that's why in UV vis, it's called that because UV is the high energy photon and vis is the low energy photon. And UV vis, even though you don't call it fluorescence, detects conjugation because that's when you'll see UV getting absorbed and visible light getting emitted.
Okay. How about mass spectroscopy?
That's all of that stuff has to do with uh basically running it through first there's different steps, but ultimately that involves magnetic field uh causing a deflection of some type of charged particle, um, which you may ionize. To get that charged particle, you can just take some atom and ionize it, but it doesn't have anything to do with photon absorption beyond that point.
What's the purpose of mass spec? Why is it so useful?
Well, it lets you so like so like Manhattan Project, we had uranium 238, uranium 235. Only one of these is fissionable. So you basically have some charged version of this, let's say, of the uranium, and you have it enter a magnetic field, and the magnetic field will cause it to deflect. So let's say we put a wall here and it'll deflect. I don't know if did we talk about magnetic fields producing centripetal motion or force?
Not really.
Okay. Well, we'll talk about that some other time then, but it produces a centripetal motion and and that's dependent on the mass, meaning the smaller mass, the more it'll get deflected. So let's say it hits here for the smaller mass, and the larger mass will get deflected less so and goes here. So here we could put a container, here we could put a container, and here is where the U 238 will be, and here's where the U 235 will be. Meaning that what is it? Um the fissionable one is the U235, and that's very not abundant. Uranium 238 is the one that's abundant. So in the Manhattan Project, when we were trying to get uranium 235, they used mass spectroscopy to separate things based on masses, and that's how we got enough U 235.
Mhm. Okay. Um, let's just keep going if possible
Uh-huh.
because I'm feeling it this session.
All
It's gonna be one of the ones I look back on
right.
and I'm like, yeah, some high yield stuff too. Okay. Next extraction.
Mhm.
So here there's a reaction between amine and carboxylic acid anhydride.
Um, okay, so which extraction procedure will completely separate an amide from the byproduct of the reaction between an amine and excess carboxylic acid anhydride? So, first of all, let's see what they're like actually asking us here, right? So they're saying
Mhm.
that they're doing a reaction between an amine, which I can write as like R, like whatever, NH2, plus um so also what like do you know what these could look like, for instance, like carboxylic acid anhydride?
Yeah, yeah.
All right, what would it look like?
I mean, say we got like an ester, but instead of the R, it's another acyl group, so to speak, like RCO or whatever,
Like this?
like that. Yeah, and then yeah, R. Yeah.
Okay. Amine, so when you have um your acid anhydride, so this is the so this covers like extraction, which is what?
Extraction is how we separate compounds. There's like a polar and non-polar layer.
Yeah. So you want yeah, so you'll have like an aqueous polar layer and like a organic non-polar layer, and you're separating things on their solubility, differential solubilities between the things.
Yeah.
So okay. So okay, we understand that. Now we're taking an amine and we're reacting it with this carboxylic acid anhydride. What happens when you do that?
So you got the electron group on the amine. It's gonna attack one of the electrophilic carbonyls.
Yeah.
Um, double bond will get bumped up. The electrons will get bumped up to oxygen, which makes it negative technically. But then you have like a yeah. So like yeah,
What would it
to draw it. It would be aqueous.
so so like what type of and this is the topic of carboxylic acid derivatives. So an amine, when you add an amine to an anhydride, you get one of those carboxylic acid derivatives, right?
An amide.
Yes. So that could look like that, right?
Mhm.
Okay. So, and they said that the amide is produced, but there's a byproduct as well here, isn't there?
Mhm.
What can that be?
COH.
Carboxylic acid, right?
Yeah.
Okay. So we have our amine, we have our carboxylic acid anhydride, we have the product amide, and we have the byproduct carboxylic acid. I drew that poorly, but carboxylic acid. We also have excess carboxylic acid anhydride that we have to deal with. So, yeah, what can we do here?
Um, so we want to separate the amide. So um
So all the choices seem to start off by saying quench unreacted anhydride. So this we have excess of. So for the excess, how do we, get rid of it?
Yeah, we would basically have to.
It seems like we have either the option of using an acid or using a base.
We use the base. That's going to take the H off this carboxylic acid and make it aqueous.
Well, we're talking first about the unreacted anhydride.
Well, I mean, I don't even like. What do you mean by unreacted hydride? Like,
So this anhydride we had excess of, right?
oh,
So there's still leftover because the amine's going to get used up, right? But the anhydride we're going to have an excess of, so we need to quench it somehow. So we can
yeah.
use.
I think of quench is like when something is like, you know, like you make something that's an ion, you make it neutral.
So that could be something that we can do. Um, but quench is just to like kind of stop something. Um, like quench your thirst or something, right? So how do we make this so the anhydride, we don't have to worry about it necessarily having a charge at this point or not. We just know that it's reactive and we want to make it no longer reactive.
I mean,
And
I guess if you add HCl, right, it's the Cl is gonna attack the anhydride.
so so since these are all carboxylic acid derivatives, they're going to behave similarly to carboxylic acids in a way, meaning that they're going to be a little bit more acidic than basic. So the first thing to do, like we have the choices of either sodium hydroxide or hydrochloric acid. It's going to be the, what do you think?
Base.
Hmm. Yes. So get rid of these guys. So the base is going to quench that unreacted anhydride. And then it seems like they say diethyl ether to separate the layers, and that the amide can be either in the ether layer or the aqueous layer. Oh, and then it says by neutralizing it with HCl and by evaporating the solvent. So let's think about um okay, the diethyl ether part would be would that be like the aqueous layer or like the organic, nonpolar layer?
Organic.
Good. All right. And what could be in that layer? Sorry. So the amide would be in which layer?
Uh, the polar one.
So generally speaking, sure, we could say an amide is polar. Um, but from this base that we initially added, that's going to actually deprotonate the carboxylic acid byproduct, right?
Mhm.
So then it's a matter of separating the amide from the carboxylic acid byproduct.
Mhm.
So which one, when you're comparing these two, which one would be more likely to be in the aqueous layer?
The carboxylic acid, of course. Yeah.
So that's gonna be it.
Hmm.
So yeah.
Okay.
So basically, here first we had to understand that because it's not like a straightforward way of wording it. They said separate an amide from the byproduct, which we aren't given between an amine and carboxylic acid anhydride. So we start with the amine, carboxylic acid anhydride, creates the amide, which we should know, like about that. And then it makes some byproduct, and then we have to figure out what that byproduct is. We know that it's going to be carboxylic acid because essentially, I mean, this is basically attacking this, boom here, this breaks off, right?
Hmm.
That's why you get your amide here, and then this is your byproduct, right?
Yeah.
So, yep, and then we see that, all the choices have either NaOH or HCl to quench the unreacted anhydride. And we know that there's excess of that anhydride, and it's a carboxylic acid anhydride, and meaning that it's going to be more acidic than basic. So you to quench it, you use a base. So that's why we used a base, and that eliminated B and D. And then we add diethyl ether, and we know that that's the nonpolar or the organic layer. And now, while the amide group or the amide is polar, and that would lead you to think that it would be in the aqueous layer, uh, it's not as polar, or it's not. It's if something's polar, it has a partial charge, but the carboxylic acid is gonna, you know, with the NaOH, it'll get deprotonated, but it doesn't even really need that. Like it's an acid, it's going to behave as an acid behaves, which means it'll get deprotonated. So then it's a question of separating the amide from a charged thing. And the charged thing will always have a higher likelihood of being soluble in an aqueous layer.
Hmm.
Mhm.
I
And
just didn't realize that the like
yep.
carboxylic acid will be deprotonated by NaOH. So,
Yeah, but even without that, right? Even without that, we know that if something's an acid, it's going to get deprotonated,
hmm.
right? So even if we didn't have the NaOH, it should get deprotonated because that's like what it does, right?
Yeah.
The Probably sent this link to you before, but this one goes over the carboxylic acid derivatives
Okay.
and the different reactions. Like to make the anhydride, you use two carboxylic acids and heat. Um, you know,
Do I have to know all of this though, or
what's up?
do I have to know that, like all of that?
Oh yeah. So like how to make the acid derivatives. Yep.
Yeah.
Mhm.
Yeah. This I just don't. I don't know. I watched some mute video of you doing this like 3 years ago.
Oh,
You just
yeah.
crunched it out like it was like a little 1+1 problem.
Um, yeah. So did you see the video I made like on Loom? Is that where you saw it or
If I don't know what loom is. It was on YouTube.
Oh, okay.
Yeah.
So, um, yeah, okay. So like, yeah, this is something called whatever, a Wheatstone bridge. And essentially what that means is it you have a an unknown resistor and a variable resistor, and that can help you figure out the resistance of the unknown resistor. Um, and so there's Kirchhoff's rules. Mostly the loop rule is what we use here, which is, any in a circuit, any loop will have a change in voltage of 0. So we can, okay, so if we see that, also like the junction rule means that things, split once they hit a junction.
What is that current that gets split or
Yeah, current, yep. So we have our like current here, um, that gets split. I'm gonna call it I naught to be the original current. And then here, the current that goes into resistor 1 is going to be current 1. And then the current that goes into resistor R, I'm just going to say is current, just regular. Um, Now, when they hit this may appear to be a junction, but it isn't one because a voltmeter is going to be, it's going to have an infinite resistance because we don't want the current to go through it.
Mhm.
That's opposite of like an ammeter, which measures current. So you want the current to go through the ammeter. So an ammeter's resistance is 0. But a voltmeter, you don't want the current to go through. So its voltage is its resistance is infinity. So we're not having a split here. So this is not a junction here. So that means that if we say I2 goes into R2, I1 and I2 are the same.
Okay.
And same thing here. This goes here into R3, and this is not a junction, so I is equal to I3 here. Okay. And then,
Yeah.
they come back here, back into I naught, right?
Mhm.
Okay. So if we think of the loop rule, we can say that the voltage across resistor 1 is going to be equal to the voltage across this resistor over here, the unknown one here.
Yeah.
And the voltage, so I'll say voltage 1, voltage, and then voltage 2 is equal to your voltage 3. Um, and they all will, like as they go through the loop, will have, a net voltage change in voltage of 0, which means that, so like that means that we can equate the two, like because so like for instance, it'll be like V1 minus V is equal to 0. V2 minus V3 is equal to 0. Um, but we could just add the second part on both sides to get an actual equation. So V1 equals V, and then V2 equals V3.
Yeah.
Okay. Um, and then we can just use like, Ohm's law. So our V1 will just be I1 R1, and our regular V is going to be I R. And we do the same thing here for V2 and V3. So I2 R2 is equal to I3 R3. Um, and we could do like like a system of equations where you can like kind of just like either like add the equations or subtract the equations or like even like divide the equations. Um,
Mm.
right?
Yeah.
So like if I combine these, I'm gonna do it like this. So like let's say I1 R1 over this part, I2 R2 is equal to I R over I3 R3, right?
Okay.
And since we said that I1 is equal to I2, this one I really can just turn into I1, right?
Mhm.
And I is equal to I3. I could just say this is I3, right?
Yeah.
In either case, you're gonna cancel those terms, right?
Yeah.
And then we just rearrange to solve for R. So, you can multiply the R3 on both sides to get R1, R3 over R2 is equal to R.
Mm.
Okay.
Yeah.
So, yeah, so the tough, like, you're probably not going to see something like, this difficult on the test, but the part that makes it difficult is Kirchhoff's loop rule. That's the one that can be kind of difficult. But yeah, this is called a Wheatstone bridge, and you essentially just use the loop rule to figure out your unknown resistor here. And yeah, I think a key part here is that this is not a junction here.
Yeah. So like voltmeters and ammeters not are not junctions,
So
or
the
ammeters are.
well, so an ammeter is going to be in series with whatever resistor you're trying to look at. So you want the current to go through, and the voltmeter is going to be like parallel to the resistor. But yeah, you're not going to have any junctions there. A junction means that, like in this case here, oops, here just means that I naught is equal to I1 plus I, meaning that they split like this.
But when does your voltage drop versus the current drop?
Oh, so well, there isn't really so like the voltage drop is basically saying that so like this plus part and the minus part here. So the voltage is really the difference between these two. So that means that over the course, like, as it goes from here all the way back, the change in voltage is going to be zero because the voltage like is what causes like this current to kind of happen. So, um,
But I mean, this is what I'm like. What I'm referring to is this basically, like, um, this type of stuff.
oh, I see what you're saying. Got it. Yeah. So if they're in parallel, they're going to be, so if they're in series, the current will stay the same, but the voltage will change. If they're in parallel, the voltage will stay the same, but the current will be different.
So I just have to memorize that.
Yeah. Like I could like probably explain it to you like in a different way, but that would be an easier way to do it. Yeah.
Okay. Um, all right.
Mhm.
So like for this problem again, the main thing was just knowing that the current going in is the same as going out.
Oh, so I would say the main thing is the loop rule. So,
Okay. The loop rule. Okay. Yeah, so like the current going in is the same as going out. That's the loop rule.
oh no, sorry. That's the junction rule.
Oh.
So that's where, if this is I naught, this is I1,
Mm-hmm.
I just regular I, like I naught is equal to I1 plus I. So a different current, like the current actually splits. Um, but the loop rule is going to be that the loop around, let me get you something here. Okay, so go to this link.
Mm-hmm. Yeah.
Yeah, and like share screen.
Do you see it?
Yeah. So here we go. So you have this is the junction. I guess it could also be called the branch rule or whatever. But that's where this I going in is equal to the sum of everything it splits into.
Mm-hmm.
That's the junction rule. Now the loop rule here is a little different. It's the sum of the changes in potential around any closed path or loop is zero. So we can see that for voltage one here, right? It's going to be like they do it with subtracting to mean the sum of all these. So the voltage one is where we start here. Now the voltage at resistor one here, I can say V1 is equal to I, the current, times R1, right? But it also goes through the second one over here, which is going to be the same current, right? But R2.
Yeah.
Oh, that's going to be V2, by the way. V2. All right. They're making it a little bit more complicated with the second voltage source there. So if we pretend that that's not there, you would just get this. So meaning if I had this with resistor 1, resistor 2, V1 here. Oh no, say V naught. Okay. Now here, All right, let me do it like this. A voltmeter here to measure the voltage across this, a voltmeter here to measure the voltage across that. So that means that you're going to get for this, what this reading here is going to be, and let's say current is just I. So here, the voltage across one is going to be I R1. Here, the voltage across R2 is going to be I R2. And if we do V naught minus V1 minus V2, you get 0
Hmm.
because that's that loop.
Okay.
So, so in other words, V naught is equal to V1 plus V2. So
Yeah.
that's what we did for the Wheatstone bridge question. Yeah. So that's yeah. So yep. So basically we did that with this and this. So this V1 is equal to the I1 R1. This V is equal to the IR. And these are equal. And then same thing happens here. Yep.
They're equal though because
Mhm.
like yeah, I was a little confused though about that.
Yeah. So there, so let's see. So this loop here, let's see. Try, okay, so in the link, there's a question after that we can look at. This also kind of describes it because the electrostatic force is conservative. Total potential energy change for a particle completing a closed path must be 0. Therefore, the sum of the changes in potential for all circuit elements around a closed path, including batteries, resistors, capacitors, must be 0. Yep. All right. So we have this circuit on the right with two voltage sources, and we have these different statements here. So let's try this out. So let's start with, okay, so there's two voltage sources, but that's okay. Let's think about them separately. So for voltage source 1, this will be a loop.
Hmm.
Voltage source 2, this will be a loop. Okay.
Yeah.
All right. So like for voltage 1, it seems like oh, this is a little weird, but like okay, so like I'm gonna do start with I1 that goes through R1, right?
Yeah, I think if that's correct.
Mm-hmm. So
Like
minus,
option one.
yeah, so minus I1, R1, and then after R2 and I2,
The
minus
current, yeah,
2 R2 is 0.
yeah.
And then for voltage 2, it's the I1 because it goes, oh, sorry, it goes through resistor 2 and resistor 3. So this will be minus I2, R2 minus I3, R3, and that's 0
Yeah.
in that loop, right? Um, and if we simply combine the two, which is kind of like what we did with the Wheatstone Bridge one, we get uh so if we combined the V1 and the V2, we would get So let's see. Wait. V2, I1, R1, I1, R1. Let's see this. Okay, okay. Sorry. This loop, because the way that I wrote it like this is actually not going to work because we have a voltage source there, V1 there. So this is actually going to be this entire loop like that.
Mm-hmm.
That means that this goes through this R1 and R3. So this is going to be I1, R1. Right? So now if we, okay, now if I do V1, it's going to be equal to I1, R1 plus I2, R2. Here, V2 is equal to I1, R1 plus I3, R3. Now, if we want to try this out, we can do V1 minus V2, and that's going to be with the rest of these, like that and that, right? So I1, R1 plus I2, R2 minus I1, R1 plus I3, R3. These guys cancel. And then we can just subtract this and this on both sides. So this is going to be true as well, right?
Sure.
And then this one, I1 is equal to I2 plus I3. Seems to be the case because this I1, at this point, I1 goes into it, and it splits into I2 that goes into this resistor, and I3 that goes into this R3. So that's where you have, so here you have the junction rule, and then here, here, and here you have your loop rule. So both of these are going to be true, or all of these are going to be true.
Mm-hmm.
Yeah.
I'm checked out.
Yeah, yeah, yeah. So, yeah, so like you're not gonna see anything like that Wheatstone bridge problem, but I would say for the circuit stuff, yeah, to maybe like yeah, maybe next time we can do like a little bit. I can talk more a little bit about the voltmeter and meter readings and maybe like a little bit more, maybe like another thing about the loop rule or something. But yeah, it's about it. Am I still seeing you tomorrow at 6?
Yeah, yeah, yeah.